Hello, can everybody hear me? Hello,
Yes, we can hear you.
okay. Good evening, everyone, and welcome to the second session of the Quantum Cryptography and Quantum Security track under the Quantum AI Lab. This track is organized by iQafé and Bibliotheca Alexandrina in collaboration with Egypt Quantum Computing Community. Today's session is titled by Post-Quantum Cryptography, the Algorithmic Layer. Kindly ensure that your microphone remain muted throughout the session. However, you are welcome to unmute yourself to ask a question at any time. It is my pleasure now to introduce today's instructor, Ms. Raghade Nawar, who is currently pursuing her master's degree in computer science at the Arab Academy with a research focus on post-quantum cryptography.
Hello everyone, I hope you can hear me. Okay, so let's start our today's session. It's about PQC, the algorithmic layer. Okay, so what do you know about the algorithmic layer of PQC? And do you know any specific algorithm from PQC or not? Please tell me. You can unmute yourself and talk, like we can have a small conversation before we start, please. Okay, so I guess we didn't. I guess like you don't have any experience about algorithm with the PQC algorithm, so we can talk now about this part. So okay, let's start about navigating the migration from classical to quantum resistant standards. We have multiple quantum threats to public key infrastructures, as engineer SAMeh has said the last time, that we have classical security vulnerabilities, like we can get attacked from our cybersecurity or cryptography that we are working now. Just give me 1 second, please. Okay, I'm so sorry for the interruption. Okay, so we have multiple threats to our classical security that we have, like the RSA, the most well-known protocol or algorithm that we have and we are working with at the moment. It's breakable now. Actually, it's not now, it's from 94, when we were sure the algorithm had appeared, and we find out that it can break RSA through vectorization and the elliptic curve cryptography also. In prolonged time, like O time, it's or the big O n power 3, and renders the PKI obsolete. So it's very fragile at the moment, but it's we can play through the time and figure it out how we can keep the RSA working at the moment until we have quantum computers. Its impact, like the 2084-bit RSA it's breakable in hours, while we know that RSA it's breakable with the normal algorithm through billions of years. So now when RSA it's fragile, we can't work with it in the future. And we have also the symmetric key weakening, like Grover's algorithm in '96. We have a quadratic speedup for unstructured search, and it reduces the symmetric key security by half. Like we have AES 128, effective security reduced by 64-bit. So we don't have any more secure key, and symmetric key. It's now became more weak for the moment. So our mitigation that we need at the moment is AES 265-bit. It's required to have the 128-bit quantum security and to have the same effect that we had before the Grover's algorithm appears. So we have an immediate crisis, and which is a threat, huge threat, which is harvest now, decrypt later. Like our data, it's mainly being collected at the moment, and we have heard a lot of time in the social media that many of data had been leaked or being purchased around the world. So this is the threat that we are speaking about. Like we have from 2024 maybe, or 2025, like data stolen today through the RSA 2048, which is encrypted. And we have a harvesting window time, and when the quantum computers arrived at 2023, 30, sorry, or 2035. Around that time, we can have the quantum break, which is projected, so we can get decrypted and expose our data, like financial records, government secrets, medical records, nuclear waste data. We have multiple important data that we cannot hide right now from this threat. So I guess we need to learn how to migrate from classical to quantum, and hybrid period we need to have until we have serious or real quantum computers, not like simulators. So we have the mathematical foundations of PQC, the standards. We have three main families, and two other families, like we can discuss it later about them. So we have the Lattice-based, the winner, which is mainly most of the winners in this round are Lattice-based algorithms. They are based on learning and with errors, excellent performance, strong proofs. We have the Kyber and Dilithium, which they are the main algorithm that we have. We have hash-based, the conservative. It's mainly Merkle trees, minimal assumptions, and the example is Sphinx Plus, which is also people work with right now. You have the cost-based, the veteran. We will know why it's a veteran. We have the error correcting codes. It has 40 more years of confidence. Examples like Michelesi and EgQCC. Michelesi, it's a classical code and it's unbreakable. So this is why we code code-based. It's the veteran. We have the concerns about multivariate and isogeny-based. Multivariate has Rainbow, which is an algorithm. It's broken at 2022, and they're still doing a research continues. Isogeny-based, it has Psych, which is broken 2022, and it has its own security concerns because isogeny, I tried to find while I'm doing my research was the presentation. I didn't find a lot of presentations or papers or research or anything about it, so I guess it has its own concerns already. So we have the new standards NIST FIPS. Actually, it's have been published in August 2024. So what is NIST? NIST is the National Institute for Standardization Technology, if I'm correct. It has mandatory for US government use, and they have each I guess from 10 to 15 years they have like rounds. We are now in round 4. So round 3, it has its own winners, the FIPS 203 and FIPS 204 and FIPS 205. They have already its own algorithm, and they speak about it. You can find the links. I can send you to read the documentation of these algorithms more better. So the FIPS 203, it's a Melcam, original crystal Kyber, and it's mainly for key encapsulation mechanism and how you can encapsulate the key with better security. And FIPS 204, it's MLDSA, original crystals dilithium. It's primary for digital signature standard, and FIPS 205 is SLH DSA. It's Sphinx Plus and stateless hash-based signatures, which is a fallback. Okay, so we have multiple crises and multiple things to have to protect and challenges in the node life cycle. As I have said earlier, that most of the issue we have, which is data like bank data, financial data, healthcare, nuclear waste data. So it's for a very long time. We have a critical infrastructure, industrial IoT, and IoT, which is, we have like power grid or SCADA. It has 30 to 50 year operational time. We have nuclear facilities, extreme security duration, and we have constrained limited CPU and memory, makes heavy crypto difficult, and systems deployed today must operate securely past 2050. As we have said before, like many of the prediction that we have in 2030 to 2035, we're going to have a real functioning quantum computers. It will be commercialized like our normal PCs or laptops that we have, and it has been like a lot of predictions. You can find it in multiple papers speaking about this topic, so we can find that too. We have also the financial systems and the digital economy, like banking and payment. Our data spends like 7 to 10 years retention, and makes current ECH transfers vulnerable to the harvest now attacks. Mainly, I have read a lot of prediction about that part, so our data can be harvested and what we can do. Until lately, I have read that MasterCard already applied PQC in their own cards, and to prevent this threat, to make it secure for their own clients and their banks. We have blockchain and crypto, as we know that Bitcoin and Ethereum rely on ECDSA signatures, and we have an urgent need for quantum-resistant wallet addresses to prevent asset theft. Because many signatures now became more fragile, and we need something strong as the lithium to help us for like blockchain and crypto in general. And we have high frequency trading, requires data integrity, speed that PQC must match to maintain market stability. And like if I go to the stock market and to put all my information and data, like my credit card, my ID to work there, it will affect me because it's important data also. We have a telecommunication and open RAN integration. So the 5G and 6G, I have read a lot of research papers, and they speak about the future because of 5G and 6G are so much important for our network and for our work in general, as as we use mainly the internet and the telecommunication. We have integration and challenges and requirements. Key challenge, we have integrating PQC into the Open RAN interfaces without latency degradation, application protecting 5G and 6G backhaul and fronthaul, government requirement, classified communication need 25 to 75-year protection. Mainly when we see end-to-end encryption through our messaging applications like WhatsApp, Discord, Messenger, or whatever, it means it's protected with multiple security layer. But with our thread that we have right now, which is harvest now and decrypt later, it will be so much vulnerable, and we need something so much powerful to prevent this threat. So PQC layers are better now instead of classical security or cryptography layer. As we know, or I don't know if you know, yes or no, but that Apple had already implemented PQC algorithm, like I think 2 years ago or a year ago, and that is good for us, which is now we have an end-to-end encryption through iMessage, but not wise. We can say not used application like WhatsApp or Telegram or Messenger or whatever the other messaging applications. But we hope that we reach this point sooner, not late, for our timeline. So what are the best thing we can say for this slide? I can say don't put all your eggs in one basket, mainly because we work mainly at this point with lattice-based protocols or algorithms or signatures. Everything is lattice-based. We need to focus mainly with code-based cryptography. We have like a monocultural culture that we rely only on lattice-based. We need to not be in this risk. So we need to work with code-based cryptography. We have like the McAleese that I spoke about before, that it has been unbroken for like 45 years or 40 years and more. And we have a security foundation that syndrome decoding problems as NP complete, and it's very independent from the lattice-based and not lookalike. So we can have multiple families that we can work with. So this is why the code-based cryptography or code-based algorithms that are the veteran of the families. So we can speak about the EgQCC, which is a Hamming quasi-cyclic. It's also a code-based algorithm. It has a few problems we can speak about, and later on we can find out that they did multiple enhancing on it. So the performance bottleneck EgQCC is a Hamming quasi-cyclic. It's a next round 4 candidate, which is it could win, we could lose, but we hope that EgQCC can work. So it has its own high security, which as an advantage, it has small keys, IND-CCA2 secure based on well understood error correcting codes, but it's a very low speed, which is so much slower than the Kyber. This is why we prefer lattice-based codes, and it's so much slower and limiting to real life or reward enterprise adoption. So this is why people use Kyber, not EgQCC. So they did their own research, and we found out that the EgQCC optimization, EgQCC, it's the optimization of EgQCC for high performance PQC, which is this is the paper name. You can find it, or I can send it to you if you want to read it more about it. What they did, it's a methodology algorithm optimization for high performance computing, and its code-based cryptography becomes a viable competitive alternative for other schemes, and with their own optimization for this algorithm, they get a 3.6 times speed up achieved in HQC operations with the correct hardware and correct software mathematical equations, so they get the better algorithm. What they did, it was mainly about changing to high performance processors, and changing a lot of the mathematical part, but it's same family like code-based algorithm. So we have real-world performance benchmarks. They tested PQC and across a lot of heterogeneous environment like server, ARM, RISC-V, IoT, and embedded systems. Most of the servers they worked so good, and mobile little bit okay, and IoT and embedded systems was a little bit not okay because the algorithms were so much big, or making the IoT and embedded systems so slow because they are very small sizes and they can't work so good with the codes and the PQC. So mainly it's a future process, and we can hear about like we need to find good solutions for the IoT or embedded systems. So are we ready for quantum safe cybersecurity, or not us as individuals, but enterprises and the companies? Actually, it's less than 25% of the people are ready, and or people have planned to migrate to PQC, and the rest of the enterprises or the companies don't have any migration plans, mainly because people don't believe in PQC, or don't believe in quantum computers, or don't believe in quantum computing will exist in the future. So they have no migration plan, and this is so bad for the moment, because most of the what you can say, most of the indications we can find that we have already threats that it can exist, and people are already quantum computing like us. So yeah, so what are the key barriers that they have for the moment? So they have a legacy system complexity, maybe IoT performance constraints, certificate authority, infrastructure updates. So as we have said, like, yeah, if I have like an IoT or embedded system, it's so bad for them that they use quantum computers or PQC because it makes them slow, and it's so bad for them, so they can not give us the best service. We have legacy systems complexity, like they don't want to migrate their own legacy system and write a new system to work with PQC. Or certificate authority, infrastructure updates. They don't want to update their own infrastructure and to make it with PQC. So if we have a migration roadmap, so let's start with 2024 to 2035. Sorry. So they decide to do their own standards. 2024-2025 standardizations, the FIPS that I spoke about before. The FIPS published and industry pilots. A lot of companies like MasterCards. We have Google, IBM, Apple, Amazon. We have a lot of big companies that work with PQC. 2025 to 2027, they have a development like round 4, completion, software updates, like They have like up to EgQC and EgQC for round 4. And they're expecting from 2027 to 2030 at deployment that a lot of companies work with the PQC and start to integrate PQC in their own code and to make it in production and roll out hybrid certificate, for example, and working with it in their own computers and their own systems. And 2030 to 2035, in these 5 years, they're expecting migration, and which is legacy retirement and working with the actual PQC algorithm, and we have at this moment actual quantum computers and people who are quantum programmers also. So this is what is their expectation and the actual roadmap that a lot of people are predicted in multiple papers, multiple research, and multiple companies are expecting this too. And after that, they can have a quantum threat field, like actual viruses maybe working with quantum. I don't know what could be the threats after that, after the harvest now, decrypt later threat. But it could be a lot of things. So we can say that the window is closing. We need crypto that outlasts the data. And we have number one, like inventory, which is identify long-lived data like HIPAA and secrets from company secrets, military secrets, government secrets. Assess, which is test crypto agility and make an hybrid implementation. Number 3, which is adopt, integrate FIPS 203, 204, and 205 in procurement. Migration takes from 10 to 15 years. The time starts at the moment, and we need to make it like to learn and to integrate multiple algorithm, and our companies, enterprises, and the government work the best as we can to not have any secrets being leaked or to make it worse for us in the future. And that's it for the algorithmic layer. We can, if anyone has any questions, please ask.
Great, Raz. Thank you very much for this presentation. I need to ask actually the audience one question. We assume that some of you have already a background about cryptography in general, right?
Yes, I have some background. I'm not sure about that.
Okay, great, Kareem. Okay. Can you tell us from your point of view, actually, what is the difference between a classical, quote-unquote, cryptography and post-quantum cryptography presented by Raghade Nawar?
So I'm familiar with the concepts of it. So basically, it depends on the mathematical problem that the algorithm is using. So for example, for RSA, it's using factorization, which doesn't have a polynomial solution in classical world, but it has a polynomial solution in RSA. ECC, for example, elliptic curve, is solving the elliptic curve problem, which is a variation of the factorization or similar to it. But for post-quantum, it's using a different algorithm, using a different mathematical problem like the lattice problem, or I think the other one we were talking about, code-based. So it depends on the mathematical problem that it's trying to solve. you're able to hear me, right? Hello? Okay. Yes, I can.
Okay, great. One last point, actually, to add to what Raghad presented, is that a post-quantum cryptography, exactly like classical cryptography, does not need quantum computing hardware and runs on the same current classical computers that we are using. Okay, back to you, Raghad.
Yeah, thank you. Okay, so I guess we have still time. We can speak about what tools we can use for our algorithmic layer. Okay, so let me share with you. Okay, can you see my screen now?
Yes, we can.
Yeah, okay, great. Okay, so we have a library which is named libox. Okay, so it's by a group in a university, or not. It's actually not a group in university, but it's part of the people who work on it. It's a University of Waterloo in Canada, which is their group. It's Open Safe Quantum. You can Google it also. And in this presentation, you'll have the link for the group if you want to read more about their works and what they have discovered. So libox, it's a C library which is written in C. It's for prototyping and experimenting with quantum resistant cryptography. Okay, so this is my presentation outline, which is what is libox, installation and setup, cloud, open source freeware status, what you can do, community and support forums, who is using libox, because you can find other companies, maybe individuals. We can find a lot of people. We have a comparison with the similar tools. And I will show you a libox live demonstration, and later we can find conclusion and resources. So the tool overview, we have what is libox. It's an open source library, C library. It's written in C, but you can use it with different languages if you want, for quantum resistant cryptographic algorithm. The full name is Open Quantum Safe libox. It provides the production ready implementations of post-quantum cryptography algorithms, project part of the Open Quantum Safe or OQS project. Okay. How to install it? If you have Linux and Mac OS, this is the bash. The bash code. You can clone it in the repo in your computer, and you build as a directory and configure with SAMeh, and later you can build and install. And after that, you can, using the package managers, using Ubuntu or Debian, if you have any of them, and add the OQS repo. If you are using macOS, this is using package manager with Homebrew. If you are using Windows, this is also what you're gonna do. If you don't want to install it in your computer, you can use Docker. If you know how to use Docker and you have it already, you can do that too. And for me, I will use the pip install with Python because I prefer using Python and do it with Python. Okay, so this is the configuration flags, how to enable all the algorithms and disable some algorithms if you want to reduce the size, enable OpenSSL integration, like you can do whatever you like. Okay, so what is the status of this library? It has a MIT license, which is completely free and open source, and it's allowed for commercial use, modification, distribution, and it's available with the source code. It's available on GitHub. It's a public repo. It has its own binary package available for major platforms, as we have saw. It's cloud ready. You can deploy it on any cloud platform, and it's free to use. We can open here the GitHub repo if you want to. Here it is. It has every list of algorithm, encapsulation mechanism. We can find also signature schemes, stateful signature schemes, and you can find everything that you need in this repo. Okay, so next, can we find any support channels or groups if you need? Yes, in GitHub and its own documentation. And Stack Overflow, you can, if you remember what is Stack Overflow, you can also write about it and you can find a lot of people's help you out, absolutely. Okay, next, who is utilizing LibOx and how famous it is? We can find a lot of cloud providers like Cloudflare, AWS, Microsoft. They are experimenting, like in Cloudflare, OQS for HTTPS experiments, AWS for PQC integration, Microsoft for Azure experiments with PQC. Software companies like Mozilla Firefox, Google Chrome, and Apple. Security companies like Cisco. Network equipment PQC, Fortinet for firewall PQC support, and Palo Alto Networks for security appliance. Academia, we can find MIT, Stanford, and UC Berkeley. We can find the KU Leuven and TU Eindhoven. Waterloo as they are part of the OQS group. It's part of it from Waterloo, which is Institute of Quantum Computing, and it's used in research and teaching. We have government agencies like NIST, which is for reference for PQC standardization. They are using also the LibOx. NSA for evaluation and testing. European Commission, the PQC crypto project, and various national cyber agencies. So its fame and recognition, it has a lot of GitHub stores. It's a top PQC library and it's downloaded a lot and I have a lot of citations and it's integrated in multiple projects. We have awards and recognition. It's part of the NIST PQC standardization efforts and it's featured in major security conferences and recommended by industry standards bodies and widely cited in academic literature. So we have multiple tools. We're gonna make a small comparison between LibOx and the other tools. We have PQC Clean. So LibOx, it's more comprehensive and production ready. PQC Clean is focused on clean portable code. So actually it's the winner is LibOx for deployment. If you want a good deployment, PQ Clean or PQC Clean for reference. Bouncy Castle PQC. So LibOx is C library performance focused and Bouncy Castle is Java and easier integration. It depends on language preferences. So actually for me, I love working with C, so I'm gonna use for me it's LibOx. For other people could have Bouncy Castle maybe. OpenSSL PQC fork. So LibOx is standalone algorithm focused. OpenSSL is full SSL TLS stack. And winner is for flexibility LibOx. For protocols is OpenSSL. We have LibSodium, which is LibSodium is for LibOx is for PQC focused. LibSodium is classical crypto, easy to use. So it's if it's a winner, so it's different purposes. We have PQC. This is classical. If whatever you want to use, you need to find the right library. So we have the industry adoption level. It's leading PQC library actually. Most widely deployed in open source PQC library. We have industry standard for PQC integration, active development and maintenance, and strong community support. So what are the available algorithms we can find in the LibOx? We can find the key encapsulation like Kyber with all variation, and Bike, which is a part of the round 4, NIST round 4. We have the classic McAleese in multiple parameter sets. We have the EgQCC, which is also candidate in round 4. We have Nitro, we have Saber as CAMs. We have digital signatures, which is Lithium, and Falcon, which is a part of round 4. We have Sphinx Plus and Picnic and Rainbow. Does anyone have any questions?
Yes, so I have a question, please.
Yeah, okay.
So it's a little bit, it's not about this topic specifically, but I wanted to ask about hybrid algorithms. I know that there are some discussions or some details about using both PQC, since PQC is a bit new, using PQC with classical algorithms. So I'm not sure if it's this discussion has materialized to something, or is there a way we can integrate both algorithms, or does these tools support using both algorithms? How can it be used?
Actually, yes. So this it's mainly so you can put. I can show you the code after the presentation. We can discuss it later if you want to, or if
Sure,
yeah. Okay. So yeah.
We can talk later. Okay.
Yeah, we were talking after this presentation, and we can see how we can integrate the LibOx with the Python, and how we can write. Because actually, if you can see in this slide that there's a classic McAleese, which is an old classical cryptography algorithm, which we can play with its own parameter and to make it work in our favor. If you want to, yeah, but just like give me 2 minutes and we will speak about this part, okay?
Perfect, thank you.
Okay.
Rather, Karim, may I add one comment here actually?
Yeah, okay.
I understand the question actually in another way. Hybrid cryptography, actually hybrid migration, which is actually using two side by side. We'll cover this actually in the last session. In the hybrid migration approach, where you keep your classical algorithms as it is, and just put an outer layer, abstraction layer or proxy layer, using post-quantum cryptography to isolate external world from internal world. But this will, from architecture perspective, this will be covered in the last session. What Raghade will show you actually in a few minutes actually how to use both side by side.
Okay.
Thank you, Raghade. Please continue.
Yeah, okay. So we have the digital signatures, which is the lithium, crystal lithium with its own variation, and Falcon, which is algorithm came out from IBM actually, and it's a candidate in round 4. We have Sphinx, which is also a winner in this round 3, and we have Picnic and Rainbow, which is they are broken. Rainbow is broken, but it's also there. We can try with it. We have, this is a notebook link. You can find it also in the presentation. This is the resources. And as a conclusion, we can say that libx is a leading open source PQC library. It's easy to install. You can do it in whatever you want, in macOS, Windows, Linux. It's completely free and open source. Excellent community support. You can find them in whatever, like GitHub, or you can find in Slack or mailing list, but I'm not sure about that part. It's widely used in industry and academia and government. Perfect for research if you want to do more research in the future, and production ready. And that's it. Let's see the just one second. The code. Okay, so here's the installation part. You need to okay, so we're gonna make and install some dependencies because it's because I'm using Python. Most of the code in Quantum, which is in Python, so we need to install some dependencies. And after that, we're gonna build here we're gonna clone our library, and after that, we're gonna build it to make sure it's working. And we're gonna set our library path. After that, we're gonna verify that the library exists, because it's very difficult to find out if it's not yes or no, because I had a lot of problem with that. So we need to, when implement it in your notebook or your PC, you need to make sure it exists, because it can have multiple issues with that. So we're gonna set our environment. After that, we're gonna install Circ and Qiskit and Qiskit packages. Sorry, simulator. And we can find here how is that the library is installed. Here, okay. And I have like a verifying installation, like it's make sure that everything is it's installed and the Python it's working and everything is working and right. Okay, so here we can have our Kyber demo. So I have imported OQS and time, and I'm initializing my the Kyber version that I'm gonna work with. And later on, I am having the I'm gonna start time and to make sure what time that I need, and make an Alice public key and key generation time. And later on, it will show me public key size and time taken, and make Bob encapsulates the shared secret. So here we're gonna start time, and we're gonna have the encapsulation time start, and will show us the ciphertext size and shared secret size and time taken. After that, we're gonna make Alice decapsulates the shared secret and make it show us the time of ciphertext time and for the decapsulation, and make dot decap secret or ciphertext, and make sure that both secrets are matching, and we will see our performance summary. So here we can see that the algorithm is which version and our security level. So we have here the public key size and time taken for Alice to generate her own key pair, ciphertext size from when Bob encapsulated its own shared secret, and the shared secret byte is 32 byte, size is 32 bytes, and time taken it's 0.51 milliseconds. We have here Alice decapsulate, which is time taken 0.16 milliseconds, and we can find here in the verification part that is success. So they have the same shared secret, and this is the first 16 byte, and its own performance is taking no time here. Okay. So we have here the dilithium digital signatures. We're also gonna import OQS and time. So we have we're gonna make an available signatures here, OQS.get enable signature mechanisms. We're gonna see total signature available, and we're gonna use the lithium, and we're gonna make a generic key pair, and we're gonna have a public key and generation. And we're gonna make a signature message, which is hello post-quantum word, and sign, and we're gonna make sign message, and we're gonna see if the message is gonna be signed. And we will verify the signature later and see the time will take. And if we're gonna check if it's valid, yes or no, and we will test if there will be test tampering detection here, if somebody tampered our message, and we will check yes or no. So okay, here sorry. Okay, so we're gonna generate our sign key pair. Okay, so our public size key size, sorry, will be 1312 bytes, and this is the time taken 0.4 milliseconds. So we have our message here, and we will find the signature size, which is 2420 bytes. Time taken is 0.336, sorry. And we're gonna verify the signature, which is signature valid, and time taken to be verified is 2.03 milliseconds. We're gonna make a test for finding tempered message. We're gonna find this tempered and tampering detected. So the signature will be correctly rejected for tempered message. And if you can see the time, it's so small too, which is for our algorithmic layer, as we have said, that many like RSA, if we can say it's taken with our classical cryptography or classical cybersecurity, quotes on quotes, we can say that it's taken millions of years to be broken. In our quantum EgQCC, sorry, algorithm, you can find it. It's taking no time, like milliseconds. So RSA will be broken in few days or hours, which is gonna be so bad. Here you can find all the benchmark performance benchmark. Like you can see the amount of time that is taken, like multiple iteration here. You can find like how many times it's taken, milliseconds, and how it's gonna be verified, signature algorithm benchmarks, and key encapsulation. Here you can find list of algorithms being generated, which are the key encapsulation mechanism that libbox support, and also signatures also you can find. Okay, so we have here Circ Bell state that demonstrates the quantum entanglement, and we can check here a small Bell state, and you can find it with Grover algorithm here, and using Grover's algorithm, which is demonstrate the quantum search and how it will work later on with it. And the cascade also builds state and how it will work with it in teleportation also. And that's it. If you have any question, please ask. If
Yes, I have a question.
yeah,
Sorry, I'm asking a lot, but it's very interesting. So,
yeah.
regarding the benchmarks for the PQC algorithm,
Yeah.
do we have a comparison with the classical algorithm? So, does it take more time, or is it similar, or it's less? And also regarding the resources, so I'm thinking in perspective of resources utilization. Would it cost more to go to PQC, or I mean, do we need to take it into consideration, or I mean, is there any statistics, or is there anyone doing this comparison? Does it take more time and resources, or it's not, or
Okay. For my knowledge, PQC algorithms are taking no time because it's mainly in milliseconds when you perform it. In general, like what I have read and what I have saw and experimenting, which is taking no time for classical RSA maybe, or AES or DSA, DS, sorry, and it's faster to use, okay, and easy to not easy to use, but it's faster. Um, will it cost so much when to migrate from classical to PQC or the hybrid part? Little bit, because now you need to use. We don't have any officially a hardware for quantum, like to use it as our laptop or PCs. So you need to go to like a little bit of Qiskit simulator, maybe, if you want to use Qiskit platform, which is maybe a little bit pricey, but I guess the hybrid migration will happen sooner or later. And for now, we use like Collab with a few bits or something like that, but not hugely pricey part. But also, engineer SAMeh has a part of the hybrid migration gonna talk about in one of the sessions, how we can migrate sooner or later from classical to PQC, or to stop at the part of the hybrid part.
okay?
Yes,
Thank
exactly,
you.
Gerard. I may also add actually that currently there are very small differences, but the optimization is ongoing. We can state it this way.
Thank you.
Okay, so does anyone have any other questions? Yeah, okay, so we have a question in the chat. I also have a question: is the post-quantum has an application in cloud or data center security infrastructure? Yes, because as I know that AWS or Amazon and Microsoft are already working to implementing PQC algorithm in their own cloud services in Azure and AWS. So yeah, they are already they are trying now to implement it in cloud or data centers.
Also, it worth mentioning that Cloudflare as well. Cloudflare, of course, we all know Cloudflare. This is the security layer that all cloud providers are using, actually. They already did this post-quantum cryptography migration since last year. So actually, all Cloudflare infrastructure that is used to secure AWS, Azure, Google, whatever clouds, has already migrated to post-quantum cryptography.
They have all to go to TLS 1.3, right? It's implemented only in TLS 1.3, not 1.2.
This is exactly because TLS 1.2 does not support post-quantum cryptography. Exactly.
Okay.
But by the way, actually mentioning about hybrid post-quantum cryptography, Cloudflare, as we speak, actually supports post TLS 1.2 with classical RSA cryptography, and also TLS 1.3 for clients using TLS 1.3 and using post-quantum cryptography.
Okay, thank you.
You're welcome.
Okay. Yeah, about the task, I will share it after this session on Classroom, don't worry, and I'll share you the resources from GitHub. Is there any resources for this infrastructure implementation? Does Engineer SAMeh have any infrastructure resources about that part? Because I don't have any.
Okay, is there any resources for this infrastructure implementation? You mean Cloudflare? Muhammad Fargani? Is this the question?
Yeah, this is a question. Yeah, I don't know it's for Cloudflare or Azure or what, but I don't have any resources, unfortunately, about that part.
Yeah, and actually, I'll share now on the chat. Okay. First, I shared Cloudflare. This is the top actually showcase for BQC and Cloudflare, of course, and the cloud infrastructure. You will okay. This is a good question. You will find. I guess you all had access to the course repo. Okay. There is a folder called the presentation.
Yeah, okay, so I can share my screen with you now.
Yes.
Yeah,
Please.
okay, just a second. Yeah, okay. Can you see my screen?
Yes.
Just 1 second. Yeah, I will.
Presentation. The bottom file. Yes. This is article called Architect's Guide to Quantum Security. Actually, maybe it is very huge. But can you share the link on the chat?
Yeah.
You need to
Okay.
download
Just
first. This explains the three different approaches for doing this migration for cloud infrastructure and on-prem enterprise infrastructure, both. Having that said, this will actually contain folder for all presentation, for all sessions, for all tasks, for all supporting material and lab exercises, like the one you have seen today and the last session. Yes, this is a document. This will be covered actually in the last session, by the way.
Yeah, if you want to revisit our previous sessions presentation and today's presentations, you can find them in 1 Quantum Security Foundation and 2 EgQCC Quantum Safe Migration and Tools presentation. And the code, you will find it here. Try to implement it, please, at your own. And I will share everything that we have talked about today in Classroom. And feel free to ask in our WhatsApp group whatever you want about today's session or anything related to the topic. And I will try to share with you some of the research papers related to today's topic about how to see PQC in 5G. Maybe if you're interested in that, please tell me what topics you want to read about as research papers, and absolutely I will share with you the FIPS three documentation papers. And if you have any other questions, please ask them on WhatsApp. Feel free about that. And thank you.